Picture this, a vast, invisible ocean stretching across the cosmos, filled with swirling clouds of gas, dust, and energy. This is the interstellar medium, the cosmic glue that holds the universe together, yet it remains one of the most mysterious and least understood parts of space. What secrets does it hide? How does it shape the stars, planets, and even life itself? Today, we're diving into the heart of this cosmic enigma to uncover 30 mind-bending mysteries of the interstellar medium. From invisible gases to cosmic dust clouds, from the birth of stars to the echoes of ancient supernova, each mystery challenges what we think we know about the universe. So, buckle up and get ready to explore the unseen forces that shape the cosmos. By the end of this journey, you'll see the space between the stars in a whole new light. Let's begin. Now, let's turn our attention to the first mystery of the interstellar medium, the invisible gas. Imagine trying to see something that's all around you but completely invisible to the naked eye. That's exactly the challenge astronomers face when studying hydrogen gas, the most abundant element in the interstellar medium. This gas is everywhere, yet it's so elusive that it's nearly impossible to detect using traditional methods. So, how do scientists uncover something they can't see? The answer lies in radio waves. Hydrogen atoms emit faint radio signals at a specific wavelength, known as the 21-centimeter line. By tuning into these signals, astronomers can map the distribution of hydrogen gas across the cosmos, revealing its hidden structure. But here's the twist. Even with this ingenious method, much of this gas remains shrouded in mystery. Its low density and vast spread make it incredibly difficult to study in detail. Why does this matter? Because hydrogen gas is the raw material for stars, planets, and even life itself. Understanding its behavior is key to unlocking the secrets of how the universe evolves. Yet, despite decades of research, this invisible gas continues to challenge our understanding, reminding us just how much we still have to learn about the cosmic glue that holds everything together. Now, let's shift our gaze to another captivating mystery of the interstellar medium, cosmic dust clouds. Picture a vast, shadowy veil stretching across the cosmos, hiding the light of distant stars and galaxies. These clouds, made up of tiny particles no larger than a grain of sand, are more than just cosmic obstacles. They're the building blocks of the universe. But how do these minuscule specks of dust form in the harsh environment of space? Surprisingly, they're born from the remnants of dying stars. When stars reach the end of their lives, they expel material into space, including heavy elements like carbon, silicon, and iron. Over time, these elements cool and clump together, forming the dust grains we see today. What's even more fascinating is the role these dust clouds play in the birth of new stars and planets. As these particles drift through space, they gather in dense regions, creating pockets of material that can collapse under their own gravity. This collapse triggers the formation of new stars, and the leftover dust forms swirling disks around them, eventually coalescing into planets, moons, and asteroids. In a way, cosmic dust is the cosmic midwife, helping to bring new worlds into existence. Yet, despite their importance, these dust clouds remain shrouded in mystery. Their composition varies widely, containing everything from silicates to organic molecules, and their exact role in star formation is still being unraveled. Why does this matter? Because without cosmic dust, the universe as we know it wouldn't exist. It's a reminder that even the smallest particles can have a profound impact on the grand tapestry of the cosmos. And as we continue to study these enigmatic clouds, we uncover more clues about how the universe creates and evolves, one speck of dust at a time. Now, let's turn our attention to one of the most puzzling mysteries in modern astrophysics, the missing baryons. You might think we've mapped out most of the universe's ordinary matter, the stuff that makes up stars, planets, and even us. But here's the twist, a significant portion of it seems to have vanished. This is what scientists call the missing baryon problem. Baryons are particles like protons and neutrons, the building blocks of atoms, and they're supposed to account for about 5% of the universe's total mass and energy. Yet, when astronomers tally up all the visible matter in stars, galaxies, and gas clouds, they find that a large fraction of these baryons are unaccounted for. So, where are they hiding? The interstellar medium might just hold the key to solving this cosmic riddle. Scientists believe that the missing baryons could be lurking in the vast, diffuse regions of the ISM in the form of hot, ionized gas. This gas is so thin and spread out that it's incredibly difficult to detect with traditional telescopes. However, recent advancements in technology, like X-ray observatories, have started to reveal faint traces of this elusive material. These observations suggest that the missing baryons might be hiding in the warm, hot intergalactic medium, or WIM, a web of gas filaments that stretches between galaxies. But why is this so important? Because understanding where these baryons are helps us piece together the full picture of how matter is distributed in the universe. It's like trying to solve a cosmic jigsaw puzzle without all the pieces. We can't see the complete image. The ISM acts as a cosmic reservoir, holding clues to how matter cycles through the universe, from the birth of stars to the formation of galaxies. By studying the properties of this hidden gas, scientists hope to uncover not just the missing baryons, but also the processes that shape the evolution of the cosmos. As we continue to probe the depths of the interstellar medium, we're reminded that even the seemingly empty spaces between stars are teeming with secrets. The missing baryons are just one piece of a much larger puzzle, and solving it could bring us closer to understanding the intricate dance of matter and energy that defines our universe. And with every discovery, we take one more step toward unraveling the mysteries of the cosmos. Now, let's shift our gaze to another enigmatic feature of the interstellar medium, dark nebulae. These dense, shadowy clouds are like cosmic curtains, blocking the light from stars and galaxies that lie behind them. Imagine looking at the night sky and seeing patches of darkness so thick that they seem to swallow the stars whole. That's the eerie beauty of dark nebulae, but what exactly are they, and why do they hold such fascination for astronomers? Dark nebulae are regions of the interstellar medium packed with gas and dust so dense that they absorb visible light. Unlike the glowing clouds of emission nebulae, which shine brightly due to nearby stars, dark nebulae are opaque and mysterious. They are often found in areas where new stars are forming, acting as cosmic nurseries. Within these shadowy depths, gravity pulls together gas and dust, creating the conditions needed for stars to be born. But because they block light, studying them requires a different approach. Astronomers rely on infrared and radio waves to peer through the darkness and uncover the secrets hidden within. The structure of dark nebulae is both complex and fascinating. They're not uniform. Instead, they're filled with intricate filaments, knots, and voids, shaped by the interplay of gravity, magnetic fields, and turbulence. Some of the most famous dark nebulae, like the Horsehead Nebula or the Coalsack Nebula, are iconic not just for their striking silhouettes, but also for the clues they provide about the processes at work in the ISM. These regions are more than just cosmic shadows. They're laboratories where the raw materials of the universe come together to create something new. But what secrets do dark nebulae hide within their shadows? For one, they're home to some of the coldest and densest environments in the universe. Temperatures in these clouds can drop to just a few degrees above absolute zero, allowing complex molecules to form. In fact, dark nebulae are rich in organic compounds, including molecules that are essential for life, like water and amino acids. This raises intriguing questions about the role these clouds might play in the origins of life in the universe. Could the building blocks of life be forged in the icy depths of dark nebulae? As we explore these shadowy regions, we're reminded that even the darkest corners of space hold the potential for creation. Dark nebulae are not just obstacles to light, they're vital components of the cosmic cycle, shaping the birth of stars and planets. By studying them, we gain a deeper understanding of how the universe works, from the smallest molecules to the largest structures. And with every discovery, we uncover another piece of the puzzle, bringing us closer to understanding the grand tapestry of the cosmos. Next, we'll turn our attention to another force that shapes the interstellar medium: magnetic fields. These invisible lines of influence play a crucial role in guiding the movement of gas and dust, and their mysteries are just as profound as those of the dark nebulae we've just explored. Now, let's venture into the invisible yet powerful forces that shape the interstellar medium: magnetic fields. These unseen lines of influence are like cosmic puppet strings, guiding the movement of gas and dust across the vast expanse of space. While we can't see them directly, their effects are everywhere, from the swirling arms of galaxies to the birthplaces of stars. But how do these magnetic fields form, and what role do they play in the grand dance of the cosmos? Magnetic fields in the interstellar medium are generated by the motion of charged particles, such as electrons and ions, within the gas and dust. As these particles move, they create electric currents, which in turn produce magnetic fields. It's a bit like how electricity flowing through a wire can create a magnetic field around it, but on a cosmic scale. These fields are surprisingly strong, often stretching across light years and influencing the behavior of entire clouds of gas and dust. They act as cosmic sculptors, shaping the structure of the interstellar medium and guiding the flow of material. One of the most fascinating roles of magnetic fields is their impact on star formation. When a cloud of gas and dust begins to collapse under gravity, the magnetic fields within it can either help or hinder the process. On one hand, they can provide support against gravity, slowing down the collapse and creating intricate structures like filaments and sheets. On the other hand, they can channel material along their lines, funneling gas into dense regions where stars are born. This delicate balance between gravity and magnetism is crucial for understanding how stars form and evolve. But magnetic fields don't just shape the birth of stars, they also influence their surroundings. For example, they can accelerate particles to incredibly high speeds, creating cosmic rays that travel through the interstellar medium. These high-energy particles can heat the gas, ionize atoms, and even trigger chemical reactions, adding another layer of complexity to the ISM. Magnetic fields also play a role in the formation of jets and outflows from young stars, shaping the environment around them and influencing the next generation of star formation. Despite their importance, magnetic fields remain one of the most challenging aspects of the interstellar medium to study. Unlike gas or dust, they don't emit light, so astronomers have to rely on indirect methods to measure them. One common technique is to observe the polarization of light, which can reveal the orientation of magnetic fields. Another method involves studying the alignment of dust grains, which tend to line up with magnetic fields. These observations have revealed that magnetic fields are not uniform. They vary in strength and direction, creating a complex web of forces throughout the ISM. As we unravel the mysteries of magnetic fields, we gain a deeper appreciation for their role in shaping the universe. They are the silent architects of the cosmos, influencing everything from the birth of stars to the structure of galaxies. By studying them, we uncover new insights into the forces that govern the interstellar medium and the processes that drive the evolution of the universe. And with each discovery, we come closer to understanding the intricate interplay of forces that make the cosmos such a dynamic and fascinating place. Next, we'll explore another intriguing aspect of the interstellar medium: the wide range of temperatures it exhibits, from the icy cold of molecular clouds to the scorching heat of ionized gas. This temperature paradox holds clues to the dynamic nature of the ISM and its role in the cosmic cycle. Now, let's turn our attention to one of the most striking features of the interstellar medium: its incredible range of temperatures. Picture this: some regions of the ISM are so cold that they hover just a few degrees above absolute zero, while others are scorching hot, reaching temperatures in the millions of degrees. This temperature paradox is not just a curiosity, it's a window into the dynamic and ever-changing nature of the interstellar medium. At the coldest end of the spectrum, we find molecular clouds, dense regions of gas and dust where temperatures can drop to as low as 10 degrees above absolute zero. These frigid environments are the birthplaces of stars, where gravity slowly pulls material together to form the seeds of new stellar systems. The extreme cold allows molecules like hydrogen to bond and form more complex structures, setting the stage for the chemistry that will eventually lead to the creation of planets and potentially life. On the other end of the scale, we encounter the hot, ionized gas that fills much of the interstellar medium. This gas, heated by the intense radiation from young, massive stars or the shock waves of supernova, can reach temperatures of millions of degrees. In these regions, atoms are stripped of their electrons, creating a plasma that glows brightly in X-rays. This hot gas is not just a byproduct of stellar activity, it plays a crucial role in shaping the ISM, driving winds that can blow material out of galaxies and into intergalactic space. So, why does such a dramatic temperature range exist? The answer lies in the diverse processes at work within the interstellar medium. Cold molecular clouds form in regions where gas is shielded from the intense radiation of stars, allowing it to cool and condense. In contrast, hot gas is created by the energy released during the birth and death of stars. Supernova, for example, explode with such force that they heat the surrounding gas to extreme temperatures, while the ultraviolet light from young stars ionizes nearby gas, creating bubbles of hot plasma. This temperature variation is not just a random feature, it's a reflection of the ISM's dynamic nature. The interplay between hot and cold gas drives the cycle of star formation and galactic evolution. For instance, the expansion of hot gas bubbles can compress nearby molecular clouds, triggering the collapse of gas and the birth of new stars. At the same time, the cooling of hot gas over time can replenish the supply of cold gas, ensuring that the cycle continues. Understanding this temperature paradox is key to unraveling the mysteries of the interstellar medium. It reveals how energy flows through the ISM, shaping its structure and driving the processes that create stars, planets, and even the building blocks of life. By studying these extremes, we gain insights into the forces that govern the cosmos and the delicate balance that keeps the universe in motion. As we continue our journey through the mysteries of the interstellar medium, we'll next explore the origins of cosmic rays, high-energy particles that race through space, leaving their mark on the ISM and beyond. Now, let's shift our focus to another fascinating enigma of the interstellar medium: the origin of cosmic rays. These high-energy particles, racing through space at nearly the speed of light, are some of the most mysterious and powerful phenomena in the universe. But where do they come from, and what role do they play in shaping the cosmos? Cosmic rays are not rays in the traditional sense. They are actually particles, mostly protons and atomic nuclei, that have been accelerated to incredible speeds. Some of these particles carry energies millions of times greater than anything we can produce in particle accelerators on Earth. But despite their immense power, their origins have long puzzled scientists. One leading theory suggests that cosmic rays are born in the aftermath of supernova, the explosive deaths of massive stars. When a star explodes, it sends shock waves rippling through the interstellar medium, accelerating particles to extreme speeds and launching them into space. Another possible source of cosmic rays is active galactic nuclei, the supermassive black holes at the centers of galaxies. As these black holes devour surrounding material, they emit powerful jets of particles and radiation. Some of these particles could be accelerated to cosmic ray energies, contributing to the flood of high-energy particles that permeate the universe. But cosmic rays don't just travel through space, they interact with the interstellar medium in profound ways. As they move through the ISM, they collide with atoms and molecules, creating secondary particles and even triggering nuclear reactions. These interactions can produce gamma rays, neutrinos, and other forms of radiation, leaving behind a trail of energy that astronomers can detect. In fact, cosmic rays play a key role in ionizing gas in the ISM, helping to shape its structure and dynamics. The impact of cosmic rays extends far beyond the interstellar medium. When these particles reach Earth, they collide with atoms in our atmosphere, creating showers of secondary particles that rain down on the surface. While most of these particles are harmless, some can pose risks to astronauts and even affect the electronics on satellites. On a cosmic scale, cosmic rays may also influence the formation of stars and planets by heating gas in molecular clouds and altering the chemistry of the ISM. Understanding the origin and behavior of cosmic rays is crucial for unraveling the mysteries of the universe. They are a reminder of the incredible forces at work in the cosmos, from the explosive deaths of stars to the immense power of black holes. By studying these high-energy particles, we gain insights into the processes that shape galaxies, drive the evolution of the interstellar medium, and even influence the conditions necessary for life. As we continue our exploration of the interstellar medium, we'll next delve into the life cycle of the ISM, how it evolves over time from the birth of stars to the death of supernova, and how this cycle shapes the universe as we know it. Now, let's turn our attention to the life cycle of the interstellar medium, a cosmic dance of creation and destruction that shapes the very fabric of the universe. The ISM is not a static entity. It's a dynamic, ever-changing environment that plays a central role in the birth and death of stars, the formation of galaxies, and the evolution of the cosmos itself. The story begins with the birth of stars. Deep within vast molecular clouds, dense regions of gas and dust in the ISM gravity begins to pull material together. As these clouds collapse, they fragment into smaller clumps, each of which can give rise to a new star. This process is fueled by the ISM, which provides the raw materials needed for star formation. Over millions of years, these clumps grow denser and hotter until nuclear fusion ignites and a star is born. But the ISM doesn't just supply the ingredients for stars, it also shapes their development. The magnetic fields, turbulence, and chemical composition of the ISM all influence how stars form and evolve. Once a star is born, it begins to interact with the ISM in profound ways. Young, massive stars emit intense radiation and stellar winds, which can heat and ionize the surrounding gas, carving out bubbles and cavities in the ISM. These bubbles can trigger further star formation by compressing nearby gas clouds, creating a feedback loop that drives the cycle forward. Meanwhile, smaller stars like our Sun contribute to the ISM more subtly, gradually shedding material through stellar winds and planetary nebulae as they age. But the most dramatic interactions occur when massive stars reach the end of their lives. When these stars exhaust their nuclear fuel, they explode as supernova, releasing an enormous amount of energy and ejecting heavy elements into the ISM. These explosions create shock waves that ripple through the interstellar medium, compressing gas and dust and triggering the formation of new stars. The heavy elements forged in the hearts of stars, elements like carbon, oxygen, and iron, are scattered across the ISM, enriching it with the building blocks of planets and even life. This cycle of star birth and death is not just a local phenomenon, it's a universal process that shapes galaxies on a grand scale. Over billions of years, the ISM evolves as stars are born, live out their lives, and die, recycling material and energy back into the medium. This continuous cycle drives the evolution of galaxies, influencing their structure, composition, and even their ability to form new stars. In spiral galaxies like our Milky Way, the ISM is concentrated in the spiral arms where star formation is most active. In elliptical galaxies, the ISM is often more diffuse, reflecting a history of intense star formation and supernova activity. The life cycle of the ISM also has profound implications for the universe as a whole. By recycling material from dying stars, the ISM ensures that the universe is constantly replenished with the elements needed to form new stars, planets, and even life. Without this cycle, the universe would be a very different place, devoid of the diversity and complexity we see today. As we continue our journey through the mysteries of the interstellar medium, we'll next explore the complex molecules that form within the ISM, molecules that hold the key to understanding the origins of life in the universe. Now, let's shift our focus to the fascinating world of interstellar molecules, a realm where the building blocks of life are forged in the most unlikely of places. The interstellar medium isn't just a vast expanse of gas and dust. It's also home to a rich variety of complex molecules, some of which are essential to life as we know it. From water and alcohol to amino acids, these molecules form in the cold, harsh environment of space, challenging our understanding of chemistry and offering tantalizing clues about the origins of life in the universe. At first glance, the idea of complex molecules forming in the vacuum of space might seem impossible. After all, space is an environment of extreme temperatures, intense radiation, and near-perfect emptiness. Yet, against all odds, molecules like water, methanol, and even formaldehyde have been detected in the ISM. These discoveries raise a profound question. How do such intricate molecules come to exist in such an unforgiving environment? The answer lies in the unique conditions found within molecular clouds, dense regions of the ISM where temperatures can drop to just a few degrees above absolute zero. In these frigid environments, atoms and simple molecules can stick together on the surfaces of tiny dust grains, forming icy coatings. Over time, chemical reactions occur on these icy surfaces, allowing more complex molecules to form. Radiation from nearby stars can also play a role, providing the energy needed to drive these reactions. In some cases, shock waves from supernova or stellar winds can further accelerate the process, creating even more complex compounds. One of the most remarkable discoveries in the ISM is the presence of amino acids, the building blocks of proteins and, by extension, life itself. While amino acids have not yet been directly detected in the ISM, simpler molecules like glycine, a basic amino acid, have been found in comets and meteorites, which are thought to originate from the ISM. This suggests that the raw ingredients for life may be scattered throughout the cosmos, waiting for the right conditions to spark the emergence of living organisms. The significance of these interstellar molecules extends far beyond their chemical complexity. They provide a glimpse into the processes that may have seeded life on Earth and potentially other worlds. Water, for example, is essential for life as we know it, and its presence in the ISM suggests that it could be abundant throughout the universe. Similarly, the discovery of organic molecules like methanol and formaldehyde hints at the possibility of prebiotic chemistry occurring in space, laying the groundwork for life to emerge on planets orbiting distant stars. But the mystery of interstellar molecules doesn't end with their formation. Scientists are still trying to understand how these molecules survive the harsh conditions of space and how they might be delivered to planets. Some theories suggest that comets and asteroids, which form from the same material as the ISM, could act as cosmic couriers, transporting these molecules to young planets during the early stages of their formation. This process could have played a crucial role in bringing the ingredients for life to Earth billions of years ago. As we continue to explore the interstellar medium, the discovery of complex molecules reminds us of the incredible complexity and resilience of the universe. These molecules are more than just chemical curiosities. They are the threads that connect the cosmos to the origins of life itself. And as we unravel their secrets, we come one step closer to answering one of humanity's oldest questions. Are we alone in the universe? Next, we'll turn our attention to the bubbles and cavities that dot the interstellar medium, created by the explosive power of supernova and stellar winds. These structures play a crucial role in shaping the ISM and driving the cycle of star formation, offering yet another layer of mystery to explore. Now, let's venture into the dynamic and ever-changing landscape of interstellar bubbles, vast, hollowed-out regions within the interstellar medium that tell the story of cosmic explosions and the relentless energy of stars. These bubbles, sculpted by the powerful forces of supernova and stellar winds, are more than just empty spaces. They are active players in the life cycle of galaxies, shaping the environment around them in profound ways. Imagine a star many times more massive than our Sun, reaching the end of its life in a spectacular explosion known as a supernova. The energy released in this cataclysmic event is staggering, sending shock waves rippling through the surrounding interstellar medium. These shock waves sweep up gas and dust, compressing them into dense shells that form the walls of a bubble. Over time, this bubble expands, carving out a cavity in the ISM that can stretch for hundreds of light years. But supernova aren't the only architects of these cosmic structures. Massive stars, even before they explode, emit powerful stellar wind streams of charged particles that flow outward at incredible speeds. These winds push against the surrounding gas, creating smaller bubbles that can merge with others or grow larger over time. Together, supernova and stellar winds create a network of bubbles and cavities that crisscross the interstellar medium, leaving behind a tapestry of voids and shells. The structure of these bubbles is as fascinating as their origins. The outer edges are often marked by shock fronts, where the expanding bubble collides with the surrounding gas, heating it to extreme temperatures and ionizing it. Inside the bubble, the gas is much hotter and less dense, creating a stark contrast with the cooler, denser material outside. This difference in temperature and density plays a crucial role in how the bubble interacts with its environment. One of the most intriguing aspects of interstellar bubbles is their ability to influence star formation. As a bubble expands, it compresses the gas and dust in its path, triggering the collapse of molecular clouds and the birth of new stars. In this way, bubbles act as cosmic catalysts, turning the destructive energy of supernova and stellar winds into the creative force that gives rise to new stellar systems. At the same time, the hot gas inside a bubble can prevent further star formation by heating the surrounding medium, creating a delicate balance between creation and destruction. The expansion of these bubbles doesn't last forever, though. Over time, the energy driving the expansion dissipates and the bubble slows down, eventually merging with the surrounding ISM. This process recycles material back into the interstellar medium, enriching it with heavy elements forged in the hearts of stars. These elements, scattered throughout the ISM, become the building blocks for future generations of stars and planets. Interstellar bubbles also serve as cosmic laboratories, offering scientists a glimpse into the physical processes that shape the universe. By studying the structure and evolution of these bubbles, astronomers can learn more about the life cycles of stars, the dynamics of the ISM, and the forces that drive galactic evolution. Each bubble tells a story of destruction, creation, and the endless cycle of cosmic renewal. As we continue to explore the mysteries of the interstellar medium, these bubbles remind us of the interconnectedness of the universe. They are not isolated phenomena but part of a larger web of interactions that shape the cosmos on every scale. And as we unravel their secrets, we gain a deeper understanding of the forces that have shaped our own corner of the galaxy. Next, we'll turn our attention to the local bubble, a region of hot, low-density gas that surrounds our solar system and holds clues to the history of our cosmic neighborhood. Now, let's zoom in closer to home and explore the local bubble, a fascinating region of hot, low-density gas that envelops our solar system. This cosmic neighborhood, stretching over hundreds of light years, is a unique feature of the interstellar medium that holds secrets about our own place in the galaxy. But how did this bubble form, and what does it mean for us here on Earth? The story of the local bubble begins millions of years ago with a series of supernova explosions in our galactic vicinity. These cataclysmic events, occurring within a relatively short span of cosmic time, released immense amounts of energy, carving out a vast cavity in the interstellar medium. The shock waves from these explosions swept through the surrounding gas, heating it to extreme temperatures and pushing it outward, creating the low-density region we now call the local bubble. Over time, as the energy from the supernova dissipated, the bubble stabilized, leaving behind a hot, tenuous gas that surrounds our solar system. One of the most intriguing aspects of the local bubble is its impact on Earth and the solar system. The bubble's hot, ionized gas acts as a protective barrier, shielding us from some of the harsher conditions of the interstellar medium. For instance, it helps deflect cosmic rays, high-energy particles that can pose risks to both technology and life. Without the local bubble, our solar system would be more exposed to these particles, potentially affecting everything from satellite communications to the Earth's climate. But the local bubble isn't just a passive shield, it's also a dynamic environment that continues to evolve. The bubble's boundaries are constantly shifting as it interacts with the surrounding interstellar medium, creating regions of turbulence and compression. These interactions can trigger the formation of new stars and influence the distribution of gas and dust in our galactic neighborhood. In this way, the local bubble plays a role in shaping the cosmic landscape around us. Scientists are particularly interested in studying the local bubble because it offers a unique opportunity to understand the processes that shape the interstellar medium on a smaller, more manageable scale. By analyzing the properties of the gas within the bubble, astronomers can gain insights into the effects of supernova, the behavior of hot gas, and the dynamics of interstellar turbulence. These studies not only help us understand our own cosmic environment, but also provide clues about how similar processes operate in other parts of the galaxy. One of the key questions surrounding the local bubble is how long it will last. Over time, the bubble's hot gas will cool and mix with the surrounding medium, gradually losing its distinct identity. But for now, it remains a defining feature of our cosmic neighborhood, a reminder of the powerful forces that shape the universe on both large and small scales. As we continue to study the local bubble, we uncover more about its origins, its impact on our solar system, and its role in the broader context of galactic evolution. This region of space, so close to home yet filled with mysteries, serves as a testament to the interconnectedness of the cosmos. And as we unravel its secrets, we gain a deeper appreciation for the delicate balance that allows life to thrive in our corner of the universe. Next, we'll dive into the chaotic motions of interstellar turbulence, a phenomenon that shapes the structure of the interstellar medium in ways that are both beautiful and bewildering. Now, let's turn our attention to the chaotic and mesmerizing world of interstellar turbulence, a phenomenon that adds both beauty and complexity to the interstellar medium. Imagine the vast expanse of space not as a serene, empty void, but as a dynamic, ever-changing ocean of gas and dust, swirling and churning in ways that defy simple explanation. This is the enigma of interstellar turbulence, a force that shapes the very fabric of the cosmos. Interstellar turbulence arises from a variety of sources, each contributing to the chaotic motions within the interstellar medium. One of the primary drivers is the energy released by supernova explosions, which send shock waves rippling through the surrounding gas. These shock waves compress and heat the gas, creating regions of intense motion and instability. Additionally, the gravitational pull of massive objects like stars and black holes can stir up the interstellar medium, generating turbulent flows that ripple across vast distances. Even the rotation of galaxies themselves contributes to this cosmic chaos, as the swirling motion of stars and gas creates eddies and currents on a galactic scale. The effects of interstellar turbulence are profound, influencing everything from the formation of stars to the structure of entire galaxies. turbulence plays a crucial role in the collapse of gas clouds, which are the birthplaces of new stars. As turbulent motions compress and fragment these clouds, they create dense pockets of gas that can eventually collapse under their own gravity, igniting the process of star formation. Without turbulence, the interstellar medium would be far more uniform, and the formation of stars would be a much rarer event. But turbulence doesn't just shape the birth of stars, it also affects their lives and deaths. The chaotic motions within the interstellar medium can disrupt the flow of gas around young stars, influencing how they grow and evolve. In some cases, turbulence can even trigger the formation of massive stars, which burn brightly and die young, leaving behind spectacular supernova remnants that further stir up the interstellar medium. This creates a feedback loop where turbulence both shapes and is shaped by the stars it helps create. On a larger scale, interstellar turbulence influences the structure of galaxies themselves. The swirling motions of gas and dust can create intricate patterns, from delicate filaments to vast, sweeping arcs. These structures are not just beautiful to behold, they also play a critical role in the evolution of galaxies. Turbulence helps distribute energy and matter throughout the interstellar medium, regulating the growth of galaxies and the formation of new stars. In this way, turbulence acts as a cosmic sculptor, shaping the universe on both small and large scales. Understanding interstellar turbulence is no easy task, as it involves complex interactions between gas, dust, magnetic fields, and gravity. Scientists use a combination of observations and computer simulations to study this phenomenon, piecing together the intricate dance of forces that drive the chaotic motions within the interstellar medium. These studies reveal that turbulence is not just random noise, it follows certain patterns and laws, much like the turbulence we see in Earth's atmosphere or oceans. By uncovering these patterns, astronomers can gain deeper insights into the processes that shape the universe. As we continue to explore the mysteries of interstellar turbulence, we uncover more about its role in the cosmos. From the birth of stars to the evolution of galaxies, turbulence is a fundamental force that shapes the universe in ways we are only beginning to understand. It's a reminder that even in the vastness of space, chaos and order are intertwined, creating a dynamic and ever-changing cosmos. Next, we'll explore the flow of gas and dust through the interstellar medium, known as the interstellar wind, and how it interacts with our solar system. Now, let's shift our gaze to the interstellar wind, a subtle yet powerful force that flows through the vast expanse of the interstellar medium. Picture this, a steady stream of gas and dust moving silently through the cosmos, shaping the environment around stars and planets. This interstellar wind is not just a gentle breeze, it's a dynamic flow that carries with it the building blocks of the universe. The interstellar wind is composed primarily of hydrogen and helium, the most abundant elements in the universe, along with traces of heavier elements and tiny dust particles. These particles, though small, play a significant role in the cosmic ecosystem. The wind moves at speeds ranging from tens to hundreds of kilometers per second, driven by the energy of supernova, stellar winds, and the gravitational pull of massive objects. Its direction is influenced by the structure of the galaxy, often flowing along the spiral arms or being channeled by magnetic fields. One of the most fascinating aspects of the interstellar wind is its interaction with our solar system. As the Sun moves through the galaxy, it encounters this flow of gas and dust, creating a boundary known as the heliosphere. The heliosphere acts like a protective bubble, shielding the solar system from the full force of the interstellar wind. At the edge of this bubble, the solar wind, a stream of charged particles emitted by the Sun collides with the interstellar wind, creating a region of turbulence and compression known as the heliopause. This boundary marks where the influence of the Sun ends and the interstellar medium begins. The interstellar wind doesn't just stop at the heliopause, it continues to exert its influence. Dust particles carried by the wind can penetrate the heliosphere, entering the solar system and contributing to the formation of comets and other small bodies. These particles also carry with them clues about the composition and history of the interstellar medium, offering scientists a glimpse into the processes that shape the cosmos. But the interstellar wind's impact goes beyond our solar system. It plays a crucial role in the evolution of galaxies, transporting material from one region to another and influencing the formation of stars and planets. In regions where the wind is particularly strong, it can compress gas clouds, triggering the birth of new stars. In other areas, it can sweep away material, leaving behind voids that shape the structure of the galaxy. This constant flow of gas and dust is a reminder that the universe is in a state of perpetual motion, with the interstellar wind acting as a cosmic conveyor belt. Understanding the interstellar wind is no simple task. Scientists use a combination of observations and simulations to study its properties, from its speed and direction to its interaction with other cosmic forces. Spacecraft like Voyager 1 and 2, which have crossed the heliopause, provide valuable data about the conditions at the edge of the solar system. These missions, along with ground-based observations, help us piece together the complex dynamics of the interstellar wind and its role in the cosmos. As we continue to explore the mysteries of the interstellar wind, we gain a deeper appreciation for its influence on the universe. From shaping the boundaries of our solar system to driving the evolution of galaxies, this cosmic flow is a testament to the interconnectedness of all things in space. It's a reminder that even the gentlest breeze in the cosmos can have a profound impact on the grand tapestry of the universe. Next, we'll delve into the varying density of the interstellar medium, exploring how its fluctuations shape the birth of stars and the evolution of galaxies. Now, let's turn our attention to the ever-changing density of the interstellar medium, a feature that plays a pivotal role in shaping the cosmos. Imagine the interstellar medium as a vast, uneven ocean, with regions so sparse they feel almost empty, and others so dense they seem to pulse with potential. This variation in density isn't random, it's a key driver of some of the most dramatic processes in the universe, from the birth of stars to the evolution of entire galaxies. At its thinnest, the interstellar medium can be almost imperceptible, with just a few atoms per cubic meter. These sparse regions, often found in the voids between stars and galaxies, are like cosmic deserts, vast, quiet, and seemingly lifeless. Yet, even here, the interstellar medium holds secrets. These low-density areas are crucial for understanding the large-scale structure of the universe, as they mark the boundaries where galaxies and galaxy clusters meet the emptiness of intergalactic space. On the other end of the spectrum are the dense molecular clouds, regions where the interstellar medium becomes so thick that it blocks out starlight entirely. These clouds are the nurseries of the cosmos, where gas and dust come together under the pull of gravity, collapsing into clumps that eventually ignite as new stars. The density here can reach millions of particles per cubic meter, creating an environment rich with the raw materials needed for star formation. It's in these dense clouds that the universe's most spectacular light shows begin, as stars burst into life, illuminating the darkness around them. The density of the interstellar medium doesn't just determine where stars are born, it also influences how they form. In regions of moderate density, stars tend to form in isolation or small groups, like solitary islands in a cosmic sea. But in the densest molecular clouds, stars are born in clusters, sometimes hundreds or even thousands at a time. These stellar nurseries are chaotic and vibrant, with young stars competing for material and shaping their surroundings with powerful winds and radiation. The density of the interstellar medium in these regions creates a feedback loop, where the formation of stars alters the environment, which in turn affects the formation of more stars. But the story doesn't end with star formation. The density of the interstellar medium also plays a crucial role in the evolution of galaxies. In spiral galaxies like our Milky Way, the densest regions are found in the spiral arms where the interstellar medium is compressed by the galaxy's rotation. This compression triggers waves of star formation, giving spiral arms their characteristic brightness and structure. In elliptical galaxies, where the interstellar medium is more evenly distributed, star formation occurs at a slower, more steady pace, shaping the galaxy's smooth, rounded appearance. Even the voids between galaxies are shaped by the density of the interstellar medium. In these regions, the low density allows galaxies to move freely, influenced only by the pull of gravity and the expansion of the universe. Over billions of years, the interplay between dense and sparse regions of the interstellar medium helps to sculpt the large-scale structure of the cosmos, creating the web-like pattern of galaxies and voids that we see today. Understanding the density of the interstellar medium is no small feat. Scientists use a variety of tools to study it, from radio telescopes that detect the faint signals of hydrogen gas to infrared observatories that peer through the dust of molecular clouds. Each observation adds another piece to the puzzle, helping us to understand how the density of the interstellar medium shapes the universe on every scale. As we explore this mystery, we're reminded of the delicate balance that governs the cosmos. From the sparse voids to the dense molecular clouds, the interstellar medium is a dynamic and ever-changing force, driving the processes that shape the universe. It's a reminder that even the smallest variations in density can have profound effects, influencing everything from the birth of stars to the evolution of galaxies. Next, we'll uncover the chemical makeup of the interstellar medium, exploring how its composition reveals the history and future of the cosmos. Now, let's shift our focus to the very building blocks of the cosmos, the chemical composition of the interstellar medium. This vast expanse of space isn't just filled with gas and dust. It's a cosmic cocktail of elements that tell the story of the universe's past, present, and future. At its core, the interstellar medium is made up of hydrogen and helium, the two lightest and most abundant elements in the universe. These elements were forged in the aftermath of the Big Bang, the explosive event that marked the birth of everything we know. Hydrogen, the simplest and most abundant element, makes up about 70% of the interstellar medium by mass. It's the fuel that powers stars, the raw material from which galaxies are built. Helium, the second most abundant element, accounts for nearly 30%. Together, these two elements form the backbone of the interstellar medium, creating a canvas on which the rest of the universe's chemistry is painted. But the interstellar medium isn't just hydrogen and helium. Scattered throughout are trace amounts of heavier elements, often referred to as metals by astronomers. These elements like carbon, oxygen, nitrogen, and iron make up less than 2% of the interstellar medium by mass, but their presence is crucial. They're the building blocks of planets, the ingredients for life, and the remnants of stars that lived and died long ago. These heavier elements were forged in the hearts of stars, created through nuclear fusion, and scattered into space when those stars exploded as supernova. Over billions of years, these elements have been recycled, mixing with the interstellar medium and seeding the next generation of stars and planets. The distribution of these elements isn't uniform. In regions where stars have recently formed and died, the interstellar medium is richer in heavier elements. These areas, often found in the spiral arms of galaxies, are like cosmic recycling centers where the ashes of old stars are used to create new ones. In contrast, regions that have seen little star formation, such as the outer edges of galaxies or the voids between them, are dominated by hydrogen and helium with only trace amounts of heavier elements. This uneven distribution tells us a lot about the history of star formation in different parts of the universe. One of the most fascinating aspects of the interstellar medium's composition is the presence of complex molecules. In the cold, dense regions of molecular clouds, atoms come together to form molecules like water, carbon monoxide, and even organic compounds like methanol and formaldehyde. These molecules are the precursors to more complex chemistry, including the amino acids that are essential for life. The discovery of these molecules in the interstellar medium has profound implications for our understanding of how life might arise elsewhere in the universe. The origins of these elements and molecules are deeply tied to the life cycles of stars. When a massive star reaches the end of its life and explodes as a supernova, it releases a flood of heavy elements into the surrounding interstellar medium. These elements mix with the gas and dust, enriching it and setting the stage for the formation of new stars and planets. Over time, this process of stellar birth, death, and recycling has shaped the chemical makeup of the interstellar medium, creating the diverse and dynamic environment we see today. Understanding the composition of the interstellar medium isn't just about cataloging elements, it's about uncovering the history of the universe. Each element tells a story, from the primordial hydrogen and helium of the Big Bang to the heavy metals forged in the hearts of stars. By studying the chemical makeup of the interstellar medium, we gain insights into the processes that have shaped the cosmos over billions of years. As we continue to explore this mystery, we'll next turn our attention to the shock waves that ripple through the interstellar medium, shaping its structure and triggering some of the most dramatic events in the universe. Now, let's dive into the dynamic and explosive world of interstellar shocks. These powerful shock waves ripple through the interstellar medium, reshaping it in dramatic ways. They are born from some of the most violent events in the universe: supernova, the explosive deaths of massive stars, and collisions between massive gas clouds. These shocks are like cosmic tsunamis, traveling at incredible speeds and leaving a trail of transformation in their wake. When a star explodes as a supernova, it releases an enormous amount of energy, sending shock waves racing through the surrounding interstellar medium. These shock waves compress the gas and dust they encounter, heating it to extreme temperatures and creating regions of high pressure. This compression can trigger the collapse of gas clouds, setting the stage for the birth of new stars. In this way, the death of one star can lead to the birth of many others, a beautiful cycle of destruction and creation. Collisions between gas clouds also generate shock waves. When two clouds collide, the impact creates a ripple effect, compressing the gas and dust at the collision site. These collisions can be incredibly energetic, producing shock waves that travel through the interstellar medium and stir up its contents. Over time, these shocks can lead to the formation of dense regions where gravity takes over, pulling material together to form new stars and planetary systems. The impact of these shock waves on the interstellar medium is profound. They not only trigger star formation but also redistribute elements throughout space. When a shock wave passes through a region, it can mix the gas and dust, spreading heavy elements forged in the hearts of stars across vast distances. This process enriches the interstellar medium, providing the raw materials for future generations of stars and planets. Without these shocks, the interstellar medium would be far less dynamic, and the universe as we know it might look very different. One of the most fascinating aspects of interstellar shocks is their ability to create complex structures within the interstellar medium. As shock waves travel through space, they can carve out bubbles and cavities, leaving behind intricate patterns of gas and dust. These structures are not just beautiful to observe, they also play a crucial role in the evolution of galaxies. By shaping the interstellar medium, shock waves influence where and how stars form, ultimately shaping the structure of galaxies themselves. The study of interstellar shocks is still a vibrant area of research. Scientists use telescopes to observe the effects of these shocks, from the glowing remnants of supernova to the turbulent regions where gas clouds collide. By understanding how these shocks work, we gain insights into the processes that drive star formation and shape the cosmos. Each shock wave tells a story of cosmic violence and renewal, a reminder of the dynamic and ever-changing nature of the universe. As we continue to unravel the mysteries of the interstellar medium, we'll next explore the ionization of gas within it, a process that reveals even more about the complex interplay of forces at work in the cosmos. Now, let's shift our focus to the electrifying mystery of ionization in the interstellar medium. Ionization is a process where atoms lose or gain electrons, transforming into charged particles known as ions. This phenomenon plays a crucial role in shaping the properties of the interstellar medium, influencing everything from its temperature to its ability to conduct energy. So, how does ionization occur in the vastness of space? One of the primary drivers is ultraviolet radiation from young, hot stars. These stars emit intense bursts of energy that strip electrons from nearby atoms, ionizing the surrounding gas. Another source of ionization comes from cosmic rays, high-energy particles that zip through the interstellar medium, colliding with atoms and knocking electrons loose. Even shock waves from supernova can contribute, heating gas to such extreme temperatures that atoms lose their electrons. The ionization process creates a mix of charged particles and free electrons, which interact in fascinating ways. For instance, ionized gas becomes highly conductive, allowing it to carry electric currents and interact with magnetic fields. This interaction can influence the movement of gas and dust, shaping the structure of the interstellar medium and even affecting the formation of stars and planets. One of the most intriguing aspects of ionization is its impact on the temperature of the interstellar medium. Ionized regions, often referred to as H2 regions, can reach temperatures of tens of thousands of degrees. These hot, glowing clouds are some of the most visually stunning features in the universe, visible through telescopes as vibrant nebulae. Yet, despite their high temperatures, these regions are also home to cooler, denser pockets of gas where new stars are born. This contrast highlights the complex and dynamic nature of the interstellar medium. Ionization also plays a key role in the chemistry of space. When atoms lose or gain electrons, they become more reactive, enabling the formation of complex molecules. This process is essential for creating the building blocks of life, such as water and organic compounds, which are found scattered throughout the interstellar medium. Without ionization, the chemical diversity of the cosmos would be far more limited. Understanding ionization is not just about studying individual atoms, it's about unraveling the larger story of how the interstellar medium functions. By observing ionized regions, scientists can map the distribution of energy and matter in space, gaining insights into the forces that drive the evolution of galaxies. Each ionized atom is a tiny piece of a much larger puzzle, helping us piece together the intricate workings of the universe. As we continue our journey through the mysteries of the interstellar medium, we'll next explore the delicate balance of pressure within it, a force that determines whether gas clouds collapse into stars or drift apart into the void. Now, let's turn our attention to the delicate dance of pressure within the interstellar medium, a force that holds the power to shape the fate of gas clouds and ultimately the stars they may become. Pressure in the interstellar medium is a balancing act, a tug-of-war between forces that can either compress gas into dense, star-forming regions or allow it to dissipate into the vast emptiness of space. At the heart of this mystery lies the interplay between two key forces, a thermal pressure and gravitational pressure. Thermal pressure is the outward push created by the heat and motion of gas particles. When gas is heated, its particles move faster, exerting more pressure and resisting collapse. On the other hand, gravitational pressure is the inward pull caused by the mass of the gas cloud itself. The more massive the cloud, the stronger its gravitational pull, which can overcome thermal pressure and cause the cloud to collapse. But there's more to this story. Magnetic fields also play a crucial role in regulating pressure within the interstellar medium. These invisible lines of force can act like a cosmic scaffolding, supporting gas clouds and preventing them from collapsing too quickly. In some cases, magnetic fields can even channel gas into specific regions, creating the conditions necessary for star formation. However, when these fields are disrupted by shock waves from supernova, for example, they can lose their stabilizing effect, allowing gravity to take over and trigger the birth of new stars. The balance of pressure isn't just a local phenomenon. It has far-reaching implications for the structure and evolution of galaxies. In regions where thermal pressure dominates, gas clouds remain diffuse and spread out, forming vast, low-density areas of the interstellar medium. But where gravitational pressure wins, gas clouds collapse, giving rise to dense molecular clouds, the nurseries where stars are born. This dynamic process shapes the distribution of matter in galaxies, influencing everything from the formation of star clusters to the creation of planetary systems. One of the most fascinating aspects of this pressure balance is its role in regulating star formation. If a gas cloud collapses too quickly, it can fragment into smaller clumps, leading to the birth of many small stars. But if the collapse is slow and controlled, it can result in the formation of massive stars which have a profound impact on their surroundings. These massive stars, in turn, can heat and ionize the surrounding gas, altering the pressure balance once again and setting the stage for future generations of stars. Understanding the mystery of pressure in the interstellar medium is key to unraveling the life cycle of galaxies. By studying how gas clouds collapse, expand, and interact, scientists can gain insights into the processes that drive the evolution of the universe. Each gas cloud, with its delicate balance of forces, is a microcosm of the larger cosmic story, offering clues to how stars, planets, and even life itself come to be. As we move forward, we'll explore another critical aspect of the interstellar medium: its role in the evolution of galaxies, a topic that ties together many of the mysteries we've uncovered so far. Now, let's shift our gaze to the grand stage of galactic evolution, where the interstellar medium plays a starring role. The interstellar medium isn't just a passive backdrop in the cosmos, it's an active participant in shaping the destiny of galaxies. From the birth of stars to the recycling of stellar material, the interstellar medium is the lifeblood of galactic transformation. At the heart of galactic evolution lies the process of star formation, and the interstellar medium is the fuel that powers it. Dense clouds of gas and dust within the interstellar medium collapse under gravity, igniting the fires of new stars. These stars, in turn, light up their galaxies, driving the cycle of creation and destruction that defines the cosmos. But the interstellar medium's role doesn't end there. When massive stars reach the end of their lives, they explode as supernova, scattering their enriched material back into the interstellar medium. This recycled material becomes the building blocks for future generations of stars and planets, ensuring that galaxies continue to evolve and grow. The interstellar medium also plays a crucial role in regulating the growth of galaxies. As stars form and die, they release energy and radiation that can heat and ionize the surrounding gas, altering its properties and influencing the rate of future star formation. This feedback loop, where the interstellar medium both fuels and is shaped by star formation, is a key driver of galactic evolution. In some cases, this process can even trigger the formation of new structures within galaxies, such as spiral arms or star-forming regions, adding to the complexity and beauty of these cosmic systems. But the interstellar medium's influence extends beyond individual galaxies. On a larger scale, the interstellar medium contributes to the flow of matter between galaxies, a process known as galactic winds. These winds, driven by supernova and the activity of supermassive black holes, can carry gas and dust out of galaxies and into the intergalactic medium. This material can eventually be recycled back into other galaxies, contributing to the growth and evolution of the universe as a whole. In this way, the interstellar medium acts as a cosmic conveyor belt, transporting matter across vast distances and shaping the large-scale structure of the universe. The long-term impact of the interstellar medium on galactic evolution is profound. Over billions of years, the continuous cycle of star formation, stellar death, and material recycling has transformed the universe from a relatively uniform sea of gas into the rich tapestry of galaxies we see today. Each galaxy, with its unique history and structure, is a testament to the interstellar medium's enduring influence. By studying the interstellar medium, scientists can trace the history of galaxies and gain insights into the processes that have shaped the universe over cosmic time. As we look ahead, the interstellar medium will continue to play a vital role in the evolution of galaxies. As galaxies collide and merge, their interstellar media will mix, triggering new bursts of star formation and reshaping their structures. In the distant future, as the universe continues to expand and evolve, the interstellar medium will remain a key player in the ongoing story of cosmic evolution. Its mysteries, though complex, offer a window into the past, present, and future of the universe, reminding us of the interconnectedness of all things in the cosmos. Next, we'll delve into the intriguing interactions between the interstellar medium and one of the most enigmatic objects in the universe, supermassive black holes. Now, let's turn our attention to one of the most fascinating and mysterious interactions in the cosmos: the relationship between the interstellar medium and supermassive black holes. These colossal objects lurking at the hearts of galaxies are not just passive consumers of matter. They are dynamic forces that shape their surroundings in profound ways. And the interstellar medium plays a critical role in this cosmic dance. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. These black holes, millions or even billions of times more massive than our Sun, are surrounded by swirling disks of gas and dust, material drawn from the interstellar medium. As this material spirals inward, it heats up, emitting immense amounts of energy and radiation. This process powers what astronomers call active galactic nuclei, some of the brightest and most energetic objects in the universe. But how does the interstellar medium feed these black holes? The answer lies in the complex interplay between gravity, magnetic fields, and the dynamics of the interstellar medium. Dense clouds of gas and dust within the interstellar medium can be pulled toward the black hole by its immense gravitational pull. As these clouds approach, they form an accretion disk, a rotating disk of material that gradually spirals inward, releasing energy as it goes. This process not only fuels the black hole, but also generates powerful jets of particles and radiation that can extend far beyond the galaxy itself. The interstellar medium doesn't just passively supply material to the black hole, it also influences how the black hole grows and evolves. For example, the density and temperature of the interstellar medium can determine how efficiently material is funneled into the black hole. In some cases, the interstellar medium can even act as a regulator, slowing down or speeding up the rate at which the black hole consumes matter. This delicate balance between supply and consumption is a key factor in the life cycle of supermassive black holes. But the relationship between the interstellar medium and black holes isn't one-sided. As black holes consume material, they release enormous amounts of energy in the form of radiation and jets. These energetic outflows can heat and ionize the surrounding interstellar medium, altering its properties and influencing the formation of new stars. In some cases, the energy released by a black hole can even push gas and dust out of the galaxy entirely, creating vast bubbles of hot gas that extend into intergalactic space. This feedback process, where the black hole both feeds on and shapes the interstellar medium, is a crucial driver of galactic evolution. The interaction between the interstellar medium and supermassive black holes also has implications for the larger structure of the universe. The jets and outflows produced by active galactic nuclei can transport material across vast distances, enriching the intergalactic medium with heavy elements and influencing the formation of other galaxies. In this way, the interstellar medium and black holes are not just local phenomena, they are part of a larger cosmic network that connects galaxies across the universe. Understanding this intricate relationship is one of the great challenges in modern astrophysics. By studying how the interstellar medium interacts with supermassive black holes, scientists can gain insights into the processes that shape galaxies and drive the evolution of the universe. It's a reminder that even the most mysterious and seemingly destructive forces in the cosmos are part of a delicate and interconnected system, where every element plays a role in the grand story of the universe. Next, we'll explore how the interstellar medium contributes to the cosmic recycling of material, a process that ensures the universe remains vibrant and ever-changing. Now, let's shift our focus to one of the most vital processes in the cosmos, the interstellar medium's role in cosmic recycling. This process is like nature's way of ensuring that nothing in the universe goes to waste. When stars reach the end of their lives, they don't simply vanish, they leave behind a legacy, enriching the interstellar medium with the building blocks of new worlds and potentially life itself. When massive stars die in spectacular supernova explosions, they release vast amounts of material into space. This material includes heavy elements like carbon, oxygen, nitrogen, and iron elements forged in the hearts of stars during their lifetimes. These elements are ejected into the interstellar medium where they mix with existing gas and dust. Over time, this enriched material becomes part of new molecular clouds, the birthplaces of future stars and planets. But the recycling process doesn't stop there. Even smaller stars like our Sun contribute to this cosmic cycle. As they age, these stars shed their outer layers, creating beautiful planetary nebulae. These nebulae are filled with elements like carbon and nitrogen, which are gently released into the interstellar medium. This gradual release ensures that even the quieter deaths of stars play a crucial role in enriching the cosmos. The interstellar medium acts as a cosmic recycling plant, gathering and redistributing these elements across galaxies. Without this process, the universe would lack the diversity of elements necessary for the formation of planets, moons, and even life. For example, the carbon in your body, the oxygen you breathe, and the iron in your blood were all once part of ancient stars. The interstellar medium is the bridge that connects the death of one generation of stars to the birth of the next. This recycling process also has profound implications for the formation of planets. When new stars form from enriched molecular clouds, they are surrounded by disks of gas and dust. These disks contain the heavy elements needed to form rocky planets like Earth. Without the interstellar medium's role in recycling, these planets and the life they might support would never come into existence. But the importance of cosmic recycling goes beyond just the formation of planets. It also influences the chemical evolution of galaxies. As the interstellar medium cycles material through generations of stars, it gradually increases the abundance of heavy elements in the universe. This process, known as chemical enrichment, shapes the composition of galaxies and determines their ability to form complex structures, including life. The interstellar medium's role in cosmic recycling is a testament to the interconnectedness of the universe. Every star that dies contributes to the birth of new stars, planets, and potentially life. It's a cycle that has been ongoing for billions of years and will continue long into the future. By understanding this process, we gain a deeper appreciation for our place in the cosmos and the intricate web of connections that bind us to the stars. Next, we'll explore how the interstellar medium plays a critical role in the birth of stars, shaping the very fabric of galaxies and the universe itself. Now, let's turn our attention to one of the most awe-inspiring processes in the universe, the interstellar medium's role in the birth of stars. This is where the magic of creation unfolds, as vast clouds of gas and dust come together to ignite the fires of new stellar systems. Without the interstellar medium, the cosmos would be a dark and empty place, devoid of the light and energy that stars provide. At the heart of star formation lies the interstellar medium's ability to gather and condense. Imagine a cosmic nursery where immense clouds of gas and dust drift through space. These clouds, often spanning hundreds of light years, are the raw materials for new stars. But how do these diffuse clouds transform into the brilliant orbs we see in the night sky? The answer lies in gravity, the invisible force that shapes the universe. When a region within a molecular cloud becomes dense enough, gravity begins to take hold. The gas and dust start to collapse inward, pulled together by their own weight. As this material contracts, it heats up, forming a dense core known as a protostar. This is the first step in the birth of a star, a process that can take millions of years. Over time, the protostar continues to gather mass from its surroundings, growing hotter and denser until nuclear fusion ignites in its core. At this moment, a new star is born, shining brightly as it begins its life cycle. But the interstellar medium doesn't just provide the raw materials for star formation. It also plays a crucial role in regulating the process. Turbulence within the clouds, caused by supernova explosions or the movement of nearby stars, can create pockets of higher density. These pockets become the seeds for new stars, ensuring that star formation occurs in a dynamic and ever-changing environment. Without this turbulence, the collapse of gas and dust would be too slow, and the universe would be far less populated with stars. The interstellar medium also influences the types of stars that form. In regions with abundant gas and dust, massive stars can take shape, burning brightly but living short, explosive lives. In contrast, areas with less material tend to produce smaller, longer-lived stars like our Sun. This diversity in star formation is a direct result of the interstellar medium's composition and distribution, highlighting its importance in shaping the cosmos. As stars form, they often do so in clusters emerging from the same molecular cloud. These stellar nurseries are some of the most spectacular sights in the universe, filled with young stars still surrounded by the remnants of their birth clouds. Over time, the radiation and winds from these new stars will blow away the remaining gas and dust, revealing the star cluster in all its glory. This process not only creates stars but also shapes the structure of galaxies, as the energy released by star formation can trigger further waves of star birth in nearby regions. The interstellar medium's role in star formation is a testament to the dynamic and interconnected nature of the universe. From the collapse of gas clouds to the ignition of nuclear fusion, every step in this process is a delicate dance of forces and materials. By understanding how stars are born, we gain insight into the origins of the light that fills the cosmos and the energy that drives the evolution of galaxies. Next, we'll explore how the interstellar medium contributes to the formation of planets, providing the raw materials for the diverse worlds that orbit stars across the universe. Now, let's shift our gaze from the birth of stars to the creation of worlds. The interstellar medium doesn't just give rise to stars, it also lays the foundation for the planets that orbit them. This is where the story of planetary systems begins, as the same clouds of gas and dust that form stars also provide the building blocks for planets. When a star is born, it's often surrounded by a swirling disk of leftover material known as a protoplanetary disk. These disks are rich in gas, dust, and ice, and they serve as the cosmic workshops where planets take shape. Over time, tiny particles within the disk begin to stick together, forming clumps that grow larger and larger. These clumps eventually become planetesimals, the building blocks of planets. Through collisions and gravitational interactions, these planetesimals merge to form protoplanets, which continue to grow until they become full-fledged planets. The composition of the interstellar medium plays a critical role in determining what kinds of planets form. In regions rich in heavy elements like carbon, oxygen, and silicon, rocky planets like Earth are more likely to emerge. These elements are essential for forming solid surfaces, atmospheres, and even the potential for life. On the other hand, in areas dominated by lighter elements like hydrogen and helium, gas giants like Jupiter and Saturn are more common. These planets are massive and lack solid surfaces, but they play a crucial role in shaping the architecture of their planetary systems. The diversity of planetary systems we observe in the universe is a direct result of the interstellar medium's varied composition. In some systems, planets form close to their stars, creating hot, rocky worlds. In others, planets form farther out where icy materials can survive, leading to the creation of gas giants and icy moons. The interstellar medium's influence doesn't stop there. It also determines the availability of water and organic molecules, which are essential for the development of life as we know it. One of the most fascinating aspects of planetary formation is how the interstellar medium contributes to the creation of habitable worlds. Water, for example, is a key ingredient for life, and it's delivered to planets through icy grains in the protoplanetary disk. These grains, formed in the cold outer regions of the disk, can migrate inward and become part of rocky planets, providing them with the water needed for oceans and atmospheres. Without the interstellar medium's role in delivering these materials, planets like Earth might never have the conditions necessary to support life. The interstellar medium also influences the long-term evolution of planetary systems. As planets form, they interact with the remaining gas and dust in the disk, shaping their orbits and influencing their final positions. This process can lead to the formation of stable, well-ordered systems like our own solar system, or chaotic, dynamic systems with planets on eccentric orbits. The interstellar medium's role in this process highlights its importance not just in the creation of planets, but in the overall structure and stability of planetary systems. As we explore the mysteries of planetary formation, we gain a deeper appreciation for the interstellar medium's role in shaping the universe. From the raw materials it provides to the complex processes it enables, the interstellar medium is at the heart of the story of planets. And as we continue to discover new worlds beyond our solar system, we're reminded of the incredible diversity and potential that the interstellar medium brings to the cosmos. Next, we'll delve into the interstellar medium's role in cosmic chemistry, exploring how it contributes to the formation of complex molecules that are essential for life and the universe itself. Now, let's turn our attention to the interstellar medium's role in cosmic chemistry, where the building blocks of life itself begin to take shape. The vast expanse of space isn't just empty, it's a cosmic laboratory where chemical reactions occur under some of the most extreme conditions imaginable. These reactions give rise to complex molecules, some of which are essential for life as we know it. In the cold, dark regions of the interstellar medium, atoms and simple molecules come together in ways that might seem impossible at first glance. Despite the harsh environment, chemical reactions thrive, driven by the energy of cosmic rays, ultraviolet light from stars, and even the shock waves from supernova. These reactions transform simple elements like hydrogen, carbon, and oxygen into more complex compounds, including water, ammonia, and even organic molecules like methanol and formaldehyde. One of the most remarkable discoveries in recent years is the presence of amino acids in the interstellar medium. These molecules, which are the building blocks of proteins, have been detected in the gas and dust clouds of space. This finding suggests that the raw materials for life may be far more widespread in the universe than we once thought. The interstellar medium acts as a cosmic factory, producing the ingredients necessary for life long before planets even form. But how do these complex molecules form in such a hostile environment? The answer lies in the unique conditions of the interstellar medium. In the cold, dense regions known as molecular clouds, temperatures can drop to just a few degrees above absolute zero. At these frigid temperatures, atoms and molecules move slowly, allowing them to stick together and form more complex structures. Dust grains in these clouds also play a crucial role, acting as tiny platforms where chemical reactions can take place. These grains provide a surface for atoms and molecules to meet, react, and eventually form more complex compounds. The implications of these chemical processes are profound. If the interstellar medium can produce complex molecules like amino acids, it raises the possibility that the seeds of life are scattered throughout the universe. When these molecules are incorporated into protoplanetary disks, they can become part of the planets that form around young stars. This means that the building blocks of life may be delivered to planets from the very beginning, setting the stage for the emergence of life. The interstellar medium's role in cosmic chemistry doesn't stop at the formation of complex molecules. It also influences the chemical evolution of entire galaxies. As stars are born and die, they enrich the interstellar medium with heavy elements forged in their cores. These elements, like carbon, nitrogen, and oxygen, are essential for the formation of more complex molecules. Over billions of years, this process of chemical enrichment shapes the composition of galaxies, making them more hospitable to the formation of planets and, potentially, life. As we explore the mysteries of cosmic chemistry, we're reminded of the interconnectedness of the universe. The interstellar medium isn't just a passive backdrop, it's an active participant in the story of life. From the simplest atoms to the most complex molecules, it plays a vital role in shaping the chemical landscape of the cosmos. And as we continue to uncover the secrets of these processes, we gain a deeper understanding of our own origins and the potential for life beyond Earth. Next, we'll explore how the interstellar medium interacts with cosmic radiation, shaping the universe in ways that are both protective and transformative. Now, let's shift our focus to the interstellar medium's fascinating role in cosmic radiation, a force that shapes the universe in ways both subtle and profound. Cosmic radiation, made up of high-energy particles like protons and atomic nuclei, travels through space at incredible speeds. These particles originate from some of the most violent events in the cosmos, such as supernova explosions and the jets of active galactic nuclei. But as they journey across the universe, they don't travel unimpeded. They encounter the interstellar medium, which acts as both a shield and a sculptor of their paths. The interstellar medium plays a crucial role in absorbing and scattering these high-energy particles. When cosmic rays collide with the atoms and molecules in the ISM, they lose energy and can even be deflected in different directions. This interaction not only slows down the particles but also transforms them, creating secondary particles that contribute to the complex web of radiation permeating space. In this way, the ISM acts as a cosmic filter, moderating the intensity and distribution of cosmic radiation throughout the galaxy. One of the most important consequences of this interaction is the protection it provides to planets and their potential for life. Without the interstellar medium, cosmic radiation would bombard planetary systems with far greater intensity, potentially sterilizing surfaces and making it difficult for life to emerge or thrive. By absorbing and scattering these high-energy particles, the ISM creates a more hospitable environment for planets, shielding them from the harshest effects of cosmic radiation. This protective role is especially critical for planets orbiting within the habitable zones of their stars, where conditions are just right for liquid water and possibly life to exist. But the interstellar medium's influence on cosmic radiation goes beyond protection. It also plays a key role in shaping the structure and evolution of galaxies. As cosmic rays interact with the ISM, they transfer energy to the surrounding gas and dust, heating it and driving turbulence within the medium. This process can trigger the collapse of gas clouds, leading to the formation of new stars and planetary systems. In this way, cosmic radiation, mediated by the ISM, becomes a driving force behind the birth of stars and the ongoing evolution of galaxies. Moreover, the interaction between cosmic radiation and the ISM has implications for our understanding of the universe's history. By studying how cosmic rays are absorbed and scattered, scientists can trace the distribution and density of the interstellar medium across vast distances. This information provides valuable clues about the conditions in different regions of the galaxy and how they have changed over billions of years. It also helps us understand the role of cosmic radiation in shaping the chemical composition of the universe, as these high-energy particles can trigger nuclear reactions that produce new elements. As we explore the mystery of the interstellar medium's role in cosmic radiation, we uncover yet another layer of its profound influence on the cosmos. From shielding planets to driving star formation, the ISM is an active participant in the grand story of the universe. And as we continue to study these interactions, we gain a deeper appreciation for the delicate balance that makes life possible and the forces that shape the universe on the largest scales. Next, we'll delve into the phenomenon of galactic winds, where the interstellar medium is propelled out of galaxies by the immense energy of supernova and black holes, reshaping the cosmos in dramatic ways. Now, let's turn our attention to one of the most dramatic phenomena in the cosmos: galactic winds. These powerful outflows, driven by the immense energy of supernova and black holes, propel the interstellar medium out of galaxies, reshaping their structure and evolution in profound ways. Galactic winds are not just a cosmic spectacle, they are a fundamental force that influences how galaxies grow, change, and interact with their surroundings. At the heart of galactic winds are the violent processes that occur within galaxies. When massive stars reach the end of their lives and explode as supernova, they release an enormous amount of energy. This energy heats the surrounding interstellar medium, creating bubbles of hot gas that expand and push outward. Similarly, supermassive black holes at the centers of galaxies can generate powerful jets and radiation, driving material away at incredible speeds. Together, these forces can launch vast streams of gas and dust into intergalactic space, forming the galactic winds we observe. The impact of these winds on galaxy evolution is immense. As the interstellar medium is blown out of a galaxy, it carries with it the raw materials needed to form new stars and planets. This loss of material can slow down or even halt star formation, effectively putting a brake on the galaxy's growth. In some cases, galactic winds can strip a galaxy of so much gas that it becomes quenched, unable to produce new stars and destined to fade over time. This process plays a crucial role in shaping the diversity of galaxies we see in the universe today, from vibrant, star-forming spirals to quiet, aging ellipticals. But galactic winds don't just take away, they also give back. As the expelled material travels through intergalactic space, it can eventually cool and fall back into the galaxy or even be captured by neighboring galaxies. This recycling of material helps to enrich the cosmic environment, spreading heavy elements forged in stars across vast distances. These elements, essential for the formation of planets and life, become part of the building blocks for future generations of stars and galaxies. The study of galactic winds also provides valuable insights into the feedback mechanisms that regulate galaxy growth. By understanding how supernova and black holes drive these outflows, scientists can piece together the complex interplay between star formation, black hole activity, and the interstellar medium. This feedback is a key factor in maintaining the balance of the universe, ensuring that galaxies don't grow too large or too quickly. Without galactic winds, the cosmos as we know it would look very different. As we explore the mystery of galactic winds, we uncover yet another layer of the interstellar medium's profound influence on the universe. From shaping the fate of individual galaxies to enriching the cosmic web, these winds are a testament to the dynamic and interconnected nature of the cosmos. And as we continue to study them, we gain a deeper understanding of the forces that drive the evolution of galaxies and the universe itself. Next, we'll investigate how the interstellar medium contributes to cosmic feedback, a process that regulates star formation and galaxy growth, ensuring the universe remains in balance. Now, let's shift our focus to a process that acts as the universe's thermostat: cosmic feedback. This intricate mechanism, driven by the interstellar medium, plays a critical role in regulating star formation and galaxy growth, ensuring the cosmos doesn't spiral out of control. Without it, galaxies might either burn too brightly with unchecked star formation or fade into obscurity, leaving the universe far less dynamic than it is today. At the heart of cosmic feedback is the interstellar medium's ability to respond to the energy and material released by stars and black holes. When massive stars explode as supernova, they inject energy into the surrounding gas, heating it up and pushing it outward. Similarly, supermassive black holes at the centers of galaxies can unleash tremendous amounts of radiation and jets, further stirring the interstellar medium. These actions create a delicate balance: too much energy and star formation is suppressed, too little, and galaxies might overproduce stars, depleting their gas reserves too quickly. One of the most fascinating aspects of cosmic feedback is its ability to self-regulate. For example, when star formation rates are high, the resulting supernova and stellar winds can heat and disperse the interstellar medium, slowing down further star formation. This creates a natural cycle where galaxies alternate between periods of intense activity and relative calm. Over time, this feedback ensures that galaxies don't grow too large or too quickly, maintaining a stable equilibrium across the universe. But cosmic feedback isn't just about slowing things down. It also plays a role in enriching the cosmos. As stars die and supernova explode, they release heavy elements like carbon, oxygen, and iron into the interstellar medium. These elements, forged in the hearts of stars, are then recycled into new generations of stars, planets, and even life. This process of enrichment is a key part of cosmic feedback, ensuring that the universe becomes more chemically complex over time. The interstellar medium's role in cosmic feedback also extends to the largest scales of the universe. By regulating star formation and galaxy growth, it influences the structure of the cosmic web, the vast network of galaxies and gas that spans the cosmos. Without this feedback, the universe might lack the diversity of galaxies we see today, from sprawling spirals to dense ellipticals. It's a reminder that even the smallest particles of gas and dust can have a profound impact on the grandest scales. As we unravel the mystery of cosmic feedback, we gain a deeper appreciation for the interstellar medium's role as a cosmic regulator. It's not just a passive backdrop to the universe's drama, it's an active participant, shaping the fate of galaxies and ensuring the cosmos remains in balance. And as we continue to study this process, we uncover new insights into how the universe maintains its delicate equilibrium, one star and one galaxy at a time. Next, we'll explore how the interstellar medium serves as a cosmic time capsule, preserving clues about the early universe and offering a glimpse into its ancient past. Now, let's turn our attention to a mystery that takes us back in time: the interstellar medium's role as a cosmic archaeologist. Imagine the ISM as a vast, ancient library, preserving the earliest chapters of the universe's story. Within its clouds of gas and dust lie clues that help us piece together the history of the cosmos, offering a glimpse into the conditions that shaped the universe billions of years ago. One of the most remarkable ways the ISM acts as a time capsule is through its chemical composition. The elements we find in the interstellar medium today, hydrogen, helium, and traces of heavier elements like carbon and oxygen, tell us about the processes that occurred in the early universe. For instance, the presence of these heavier elements, forged in the hearts of the first stars and scattered by supernova, reveals how the universe evolved from a simple, primordial state to the complex, chemically rich cosmos we see today. But the ISM doesn't just hold chemical clues, it also preserves physical imprints of the universe's early days. Tiny grains of cosmic dust, for example, can trap particles from ancient supernova or even remnants of the Big Bang itself. By studying these grains, scientists can uncover details about the temperatures, pressures, and conditions that existed in the universe's infancy. It's like finding a fossilized footprint that tells us not just about the creature that made it, but also about the environment it lived in. Another fascinating aspect of the ISM's role in cosmic archaeology is its ability to preserve light from the distant past. When light from ancient stars and galaxies passes through the interstellar medium, it interacts with the gas and dust, leaving behind a kind of fingerprint. By analyzing this light, astronomers can determine the composition, temperature, and even the motion of the ISM at different points in cosmic history. This allows us to reconstruct the universe's timeline, tracing its evolution from the Big Bang to the present day. The ISM's role as a cosmic time capsule also extends to the formation of galaxies. By studying the distribution and movement of gas in the ISM, scientists can infer how galaxies grew and changed over billions of years. For example, the way gas flows into and out of galaxies, driven by supernova and black holes, provides clues about the processes that shape their structures. This helps us understand not just how galaxies formed, but also how they continue to evolve. Perhaps most importantly, the interstellar medium's role in cosmic archaeology reminds us that the universe is deeply interconnected. The same processes that shaped the early universe, star formation, supernova, and the recycling of material continue to shape it today. By studying the ISM, we're not just looking back in time, we're also gaining insights into the ongoing story of the cosmos, one that's still being written. As we explore this mystery, we uncover a profound truth. The interstellar medium is more than just the space between stars. It's a living record of the universe's history. And by decoding its secrets, we come closer to understanding our place in the grand tapestry of time and space. Next, we'll delve into how the ISM connects to other cosmic mysteries, shedding light on the universe's greatest enigmas. Now, let's shift our gaze to one of the most intriguing intersections in the cosmos, the interstellar medium's connection to the universe's greatest mysteries. The ISM isn't just a backdrop for stars and galaxies. It's a key player in unraveling some of the most profound questions about dark matter and dark energy. These two cosmic enigmas make up the vast majority of the universe, yet they remain invisible and poorly understood. Could the interstellar medium hold the clues we need to decode them? Let's find out. Dark matter, the mysterious substance that makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. But here's where the ISM comes in. While dark matter itself remains elusive, its gravitational effects are undeniable. It shapes the distribution of gas and dust in the interstellar medium, influencing how galaxies form and evolve. By studying the movements and structures of the ISM, scientists can map the gravitational influence of dark matter, piecing together its hidden presence. It's like using the ripples on the surface of a pond to infer the shape of the stone that caused them. Then there's dark energy, the even more mysterious force driving the accelerated expansion of the universe. While dark energy operates on the largest scales, its effects ripple through the cosmos, subtly influencing the behavior of the ISM. For instance, the expansion of the universe stretches the fabric of space, altering the density and distribution of interstellar gas over time. By observing these changes, astronomers can gather indirect evidence about the nature of dark energy. The ISM, in this sense, becomes a cosmic laboratory, offering insights into forces that shape the very fabric of reality. But the ISM's role doesn't stop there. It also acts as a bridge between these cosmic mysteries and the visible universe. For example, the interaction between dark matter and ordinary matter in the ISM could reveal how these two components coexist and influence each other. Some theories suggest that dark matter particles might occasionally collide with atoms in the ISM, producing faint signals that could be detected. While such events are incredibly rare, the ISM provides the perfect environment to search for them, offering a potential pathway to finally understanding dark matter. Similarly, the ISM's response to the universe's expansion could shed light on the properties of dark energy. By measuring how gas clouds in the ISM move and evolve over cosmic time, scientists can test theories about the rate of expansion and the forces driving it. This makes the ISM not just a passive observer, but an active participant in the quest to solve these cosmic puzzles. As we explore these connections, we begin to see the interstellar medium in a new light. It's not just the space between stars, it's a dynamic, interconnected web that ties together the visible and invisible aspects of the universe. By studying the ISM, we're not only uncovering the secrets of the cosmos, but also gaining a deeper appreciation for the intricate relationships that bind it all together. Next, we'll look ahead to the future of the interstellar medium and how it will continue to shape the universe in the eons to come. As we peer into the vast expanse of the cosmos, one question looms large. What does the future hold for the interstellar medium? This cosmic tapestry, woven from gas, dust, and magnetic fields, has been a silent witness to the birth and death of stars, the formation of galaxies, and the evolution of the universe itself. But as galaxies continue to evolve and the universe expands, the interstellar medium is poised to play an even more pivotal role in shaping the cosmos in the eons to come. One of the most profound changes on the horizon is the ongoing expansion of the universe driven by dark energy. As space stretches, the density of the interstellar medium will gradually decrease, spreading its gas and dust thinner across the cosmos. This thinning will have far-reaching consequences for star formation. In the distant future, as the ISM becomes more diffuse, the birth of new stars may slow down, leading to a quieter, more subdued universe. Galaxies, once vibrant with stellar activity, could enter a phase of decline, their light dimming as the fuel for new stars dwindles. But the story doesn't end there. Even as the ISM thins, it will continue to serve as the raw material for the universe's ongoing evolution. Supernova and stellar winds will still inject energy and heavy elements into the interstellar medium, enriching it with the building blocks for future generations of stars and planets. Over billions of years, this process will recycle the remnants of dying stars, ensuring that the ISM remains a dynamic and ever-changing part of the cosmic landscape. Another intriguing possibility lies in the interaction between galaxies. As the universe expands, some galaxies will collide and merge, triggering bursts of star formation and reshaping their interstellar medium. These galactic encounters will stir up the ISM, creating turbulent regions where new stars can ignite. In this way, the interstellar medium will continue to act as a cosmic crucible, forging new stellar systems even as the universe grows older and colder. Looking even further ahead, the interstellar medium may hold clues to the ultimate fate of the universe. If dark energy continues to accelerate the expansion of space, the ISM could eventually become so sparse that it no longer supports the formation of stars or galaxies. The universe might enter a phase known as the heat death, where energy is evenly distributed and all cosmic activity ceases. Yet, even in this distant future, the interstellar medium will remain a testament to the universe's rich history, a silent archive of the processes that shaped everything we see today. The interstellar medium's future is a story of transformation and resilience. It reminds us that the cosmos is not static but constantly evolving, driven by forces both seen and unseen. As we continue to study the ISM, we gain not only a glimpse into the universe's past but also a window into its future. And in understanding its role, we come to appreciate the intricate dance of matter and energy that binds the cosmos together, shaping its destiny across the ages. As we bring our journey through the mysteries of the interstellar medium to a close, it's worth reflecting on just how much this cosmic tapestry has revealed to us. From the invisible gas that fills the void to the complex molecules that hint at the origins of life, the ISM is a treasure trove of secrets waiting to be uncovered. Each mystery we've explored, whether it's the missing baryons, the enigmatic dark nebulae, or the role of magnetic fields, has deepened our understanding of the universe and our place within it. These 30 mysteries remind us that the cosmos is far more intricate and dynamic than we often imagine, filled with processes that shape galaxies, stars, and even the potential for life itself. The interstellar medium is not just a backdrop to the universe's grand story. It's an active participant driving the birth and death of stars, the formation of planets, and the evolution of galaxies. It's a cosmic recycler, a cosmic chemist, and a cosmic historian, preserving clues about the universe's past while shaping its future. By studying the ISM, we gain insights into the forces that govern the cosmos, from the smallest particles to the largest structures. It's a reminder that the universe is a place of endless wonder, where even the spaces between stars hold profound mysteries waiting to be solved. But our exploration doesn't end here. The interstellar medium continues to challenge and inspire scientists, pushing the boundaries of what we know and what we can discover. And now it's your turn to join the journey. What mysteries of the cosmos fascinate you the most? What questions do you have about the interstellar medium or the universe at large? Share your thoughts in the comments below. We'd love to hear your ideas and continue this conversation. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update as we dive deeper into the wonders of space. Together, let's keep exploring the infinite mysteries of the universe, one discovery at a time.